Good day, everyone. We are now down to the last lecture of our meteorology class. And to inform everyone, next week we will have our midterm examination. So see you by then, and I hope you study your lessons well. The coverage of the exam starts from the very first lesson until today's discussion. So for this last topic, we're going to talk about the weather forecasting. And the basic content outline for today's discussion. We're going to start with the acquisition of weather information, and then we're going to discuss the weather forecasting tools as well as the weather forecasting methods, and we're going to talk about the types of forecasts. First is acquiring weather data. And we know that before weather can be predicted, forecasters must have an accurate picture of current atmospheric conditions. And to get this accurate picture of current atmospheric conditions, it involves collecting, transmitting, and compiling billions of pieces of observational data. And to do that, we have the World Meteorological Organization, or the WMO. It's a United Nations agency and is responsible for the international exchange of weather data. On a global scale, this task requires that data from more than 185 participating nations and 6 territories around the globe will be collected simultaneously and standardized and transmitted to the participating countries. And in collecting weather data, we have what we call the surface observations. And what you can see in these pictures, particularly in this first picture that I'm showing here, is the data buoy or data buoy. This is used to record atmospheric conditions over a section of the global ocean. And this data buoy collects and transmits via satellite to a land-based station. And accordingly, worldwide, there's about 11,000 observation stations on land and 4,000 ships at sea and 1,200 data buoys that report atmospheric conditions. And aside from these data buoys, we also have what we call the automated surface observing systems that report weather data automatically. So these automated surveying systems, as what you can see in the second picture, are equipped with a variety of instruments designed to sample the sky for cloud coverage, as well as take temperature and dew point measurements, and also to determine wind speed and wind direction, and even detect the present weather, such as whether it is raining or snowing. Aside from the surface observations, we also have observations aloft because upper air observations are essential for producing reliable forecasts, and radiosondes, for that matter, are a primary tool for gathering weather data aloft. What you can see in this picture is a radiosonde, a lightweight instrument packages, which contains sensors that is shown in here to measure temperature, humidity, and pressure. And these sensors are carried aloft by the weather balloon that is shown in here. And this radiosonde also has a radar unit for tracking the radiosonde that is shown in this arrow. So these data or the data are transmitted via radio to the local observation station that launch it, and usually a weather forecast office, of course. And this radio sound data is termed a sounding and are used to assess the stability of the air and to generate upper level maps. And despite the advances in weather data collection, there are two difficulties that remain. First is the network of weather observation stations does not provide consistent coverage around the globe, particularly over the oceans and in the remote areas. And the second difficulty to take note is observations may have inaccuracies due to instrument and or transmission error. There are more tools in weather forecasting, and that includes weather satellites. And weather satellites as tools in forecasting shows that they are invaluable tools for tracking storm systems. And as what you can see, this color composite image produced by a geostationary satellite, it shows a severe storm that crossed North America. So this is just an example. When you say weather satellites, we have two as shown in this picture. The first one is the polar orbiting satellite as shown in the upper corner. So these polar orbiting satellites circle roughly over the north and south poles. The first one was placed in 1960 into a polar orbit so that it circles Earth from roughly north to south as shown in this red arrow. A polar orbiting operational environmental satellites are low-flying satellites that orbit approximately 850 kilometers or 8 or 530 miles above Earth's surface 14 times daily. This system offers the advantage of recording images of the entire planet twice daily and covering a large region in a few hours. Also, because of their relatively low altitude, POES instruments obtain high resolution images. And the second weather satellite is shown in this lower corner is the geostationary satellite. And this geostationary satellite, as their name implies, a geostationary satellite moves at the same rate that Earth rotates and remains stationary over a fixed position on Earth's surface. So in this figure, in the second figure, the geostationary satellite, in order to remain positioned over a given site, the satellite must orbit at a greater distance. So at these higher altitudes, the GOES or the geostationary operational environmental satellites images obtained are less detailed than those captured by these polar orbiting satellites instruments. So geostationary satellites play an important role in monitoring the development and movement of tropical storms and hurricanes. From the weather satellites, we obtained different images, and we call these satellite images. We have types of satellite images, as shown in this picture as an example. This is an image of the Eastern Pacific Ocean, taken at just about the same time on the same day. The first one is showing the visible image. So the first type of satellite image is the visible images because geostationary satellites are equipped with instruments that detect sunlight reflected from the Earth and producing visible light images. So visible satellite imagery records the intensity of light reflected from cloud tops and other surfaces. So it is used to determine cloud locations and thickness during the day. And visible images are better for showing cloud patterns and storm systems such as mid-latitude cyclones and hurricanes. And as an advantage, it has a high resolution, which makes detection of smaller features possible. And as shown in this picture, the clouds in the visible image appears white, and it's superimposed on the image are the cold and warm and occluded fronts. The next type is the infrared images. So infrared images obtained from radiation emitted rather than reflected from objects. So infrared satellite imagery is used to determine cloud height during both day and night. It is actually useful in determining which clouds are most likely to produce precipitation and or stormy conditions. So a major advantage of infrared imagery is its ability to detect energy radiated skyward both day and night. And as a result, for that, the movement of storms can be monitored 24 hours a day. And as shown in this picture, the low clouds in the infrared image appear in various shades of gray, as compared to the visible images with higher resolution. These infrared images has low resolutions. Another type of satellite images is the water vapor image, as shown in this picture. So most of Earth's radiation with a wavelength of 6.7 micrometers is emitted by water vapor. And satellites equipped with detectors for this narrowband radiation are in effect mapping the concentration of water vapor in the middle and upper troposphere. And because most fronts occur between air masses having contrasting moisture conditions, these water vapor images are valuable tools for locating frontal boundaries. And as what you can see in this picture, there are some brighter the white part, the greater the atmosphere's water vapor content. And the black areas are the driest. So we continue with more forecasting tools. And in order to aid in the enormous task of weather forecasting, local weather forecast offices are equipped with an interactive computer system that is called Advanced Weather Interactive Processing System, or the AWIPS. An AWIPS workstation, as what is shown in this picture, consists of three graphical displays and usually one or more personal computers for interacting with text materials. So this advanced weather interactive processing system is a tool used by forecasters that integrates all model and observational data, including satellite and radar data, in one location. And as what you can see in this figure is just an example of a thermodynamic diagram, because forecasters typically display and analyze upper air data, or what we call soundings that are collected by radiosondes, on a type of thermodynamic diagram that is called SCUTI. And this provides a vertical profile of air and dew point temperatures through the atmosphere for a particular time and location. After knowing the different tools of forecasting, we're going to check the different methods of weather forecasting. And when you say weather forecasting, it is about making a forecast. And a weather forecast is a scientific estimate of the weather conditions at some future time. So in this point, we're going to check the modern weather forecasting. So when you say modern weather forecasting, that means numerical weather prediction, because numerical weather prediction is a technique that employs complex computer programs called forecast models to make weather forecasts. And numerical weather prediction relies on the fact that the behavior of atmospheric gases is governed by a set of fundamental physical principles or laws that can be expressed as mathematical equations, for example, the ideal gas law and the laws of thermodynamics. And so the numerical weather prediction uses highly refined computer models that attempt to mimic the behavior of the real atmosphere. And the output is a description of the future state of the atmosphere that is called the weather forecasts. And each model has a three-dimensional grid consisting of a large number of points called grid points that is separated by a defined distance. So a high-resolution model has grid points that are generally separated by less than 5 kilometers, whereas a low-resolution model might have data points located more than 300 kilometers apart. In employing the numerical prediction, the technique involves these following steps. The first one is assigning current weather measurements to each of the grid points in the forecast model. That means meteorologists begin by plugging current atmospheric conditions such as temperature, pressure, and wind into a forecast model run on supercomputers. And this is done by gathering data from as many locations as possible and interpolating these data to another selected locations. And this set of values represents the atmospheric conditions at the start of the forecast. And next to it is the computer run or a computer simulation that solves the equation. A computer simulation solves each equation for as many as 50 levels of the atmosphere. After literally billions of calculations, it generates a forecast of how these basic weather elements are expected to change over a short time frame for about 5 to 10 minutes. And this process begins again. When the new values have been calculated, steps are repeated numerous times until the end of the forecast period. That generates a forecast for the next 5 to 10 minutes. Somehow, some models produce forecasts on an hourly basis, out to perhaps 12 hours, while other models generate forecasts every 6 hours with coverage of up to 2 days or longer. And to add up, using various mathematical models, the National Weather Service of the United States produces a variety of forecast charts. And these forecast charts is what we call the prognostic charts, or simply progs. And because these machine-generated maps predict the atmospheric conditions at some future time, that's why they are called the prognostic charts. Now we know that the numerical prediction uses models to produce forecasts, and once generated, statistical methods are used to modify machine-generated numerical forecasts by making comparisons of the accuracy of previous forecast. And this approach is what we call as the model output statistics, or MOS, which attempts to correct for errors that the model tends to make consistently. So again, model output statistics, or MOS, corrects bias in the numerical model output. So this important post-processing phase in numerical prediction is necessary for continually adjusting numerical models and improving their predictability. And despite the sophistication of numerical models, most still produce forecast errors. Therefore, humans perform the final steps in weather forecasting using their experience and knowledge of meteorology. And forecasters rely on a technique known as in-symbol forecasting, and in-symbol forecasting allows meteorologists to assess uncertainty in a numerical forecast. So simply, this method involves producing a number of forecasts using the same computer model, but slightly altering the initial conditions while remaining within an error range of the observational instruments. So essentially, in-symbol forecasting attempts to assess how the inevitable errors and omissions in the weather measurements might affect forecast accuracy. We've seen the modern weather forecasting method, and there are also other forecasting methods that are available to meteorologists that we can say have stood the test of time. So the other forecasting methods that are used mainly to improve machine-generated forecasts are persistence forecasting, climatological forecasting, analog method, and trend forecasting. So for persistence forecasting, it assumes that the weather will not change over a specified period of time. And the climatological forecasting assumes that the average weather will prevail. And since this is talking about the average weather, one interesting use of climatological data is for predicting a white Christmas. That is, a Christmas with inch or more of snow on the ground. And the next one is the analog method, assumes that weather repeats itself in a predictable way. A somewhat more complex way to predict the weather, since forecasters attempt to find well-established weather patterns from the past that are similar to a current event. From that, forecasters predict how the current weather might evolve, and this analog method was the backbone of weather forecasting before the advent of computer modeling. And an analog method called pattern recognition remains an important tool for improving short-range machine-generated forecasts. And the next one is what we call the trend forecasting. So this assumes that weather systems will continue to move in the same direction and at the same rate. Because weather events tend to increase or decrease in speed and intensity or change direction, trend forecasting is most effective over periods of just a few hours, particularly well for forecasting severe weather events that are expected to be short-lived, such as hailstorms and tornadoes, because warning for these events must be issued quickly and must be site-specific. And a type of trend forecasting is a nowcasting that depends heavily on weather radar and geostationary satellites. Its primary use is to issue warnings of severe weather, such as tornadoes, hailstorms, and high winds, because such mesoscale phenomena are too small to appear on a prognostic chart. So the detection of these weather relies heavily on weather radar and geostationary satellites. So this nowcasting again is used to predict very short-lived, usually 6 hours local weather events. We've passed through the methods and the tools of forecasting, so now we're going to check the types of forecasts. So most forecasts are one of two types, either qualitative or quantitative. The qualitative forecast describes an aspect of the weather that can be observed but not easily measured or quantified. So, example, partly cloudy in the morning followed by a gradual clearing is an example of qualitative forecasts. So it can be very informative to the public. And the next one is the quantitative. So these quantitative forecasts deal with measurable weather data. And for example, a forecast predicting maximum and minimum temperatures. And this figure is showing a quantitative precipitation forecast, and it depicts the amount of liquid precipitation in inches that is expected to fall over an area within a defined time period or a period of time. So this precipitation forecast is given as a percentage of probability. That means probability of precipitation that is expressed like a 40% chance of rain. So there are also other types of forecasts that are based on the time period. First is the short range, because the forecasts only extend up to 48 hours or 2 days. Then we have the medium range, because a forecast covers period extending about 3 to 7 days into the future. And the long range This is the longest range forecast that covers the period beyond 7 days and have no outer time limit. So that is all for the types of forecasts. And to have a quick recap of the main points of the discussion today, these are some of the summary points to highlight. First is assessing current atmospheric conditions involves collecting, compiling, and transmitting billions of pieces of observational data. And the forecasting of weather by high-speed computers is known as numerical weather prediction. And so, in symbol forecasting involves producing a number of forecasts using the same computer model but slightly altering the initial conditions to assess uncertainty. And a persistence forecast is a prediction that future weather will be the same as the present weather, and whereas a climatological forecast is based on a climatology of a particular region. And lastly, a type of trend forecasting called nowcasting is used to forecast very short-lived, usually 6 hours localized weather events. So these are just some of the few points that we need to remember for today's discussion. Thank you so much for your attention and listening, and see you soon.